In this problem, we have a wheel that is rotating about a fixed center because it's fixed here. And it has an angular velocity of omega that equals to 0.2 theta squared. Theta is the angular displacement in radian. And we need to determine the magnitude of linear velocity and linear acceleration of the point P on this wheel after the wheel has turned 1 revolution. And what is 1 revolution? That is when theta, the angular displacement, equals to 2 pi. So in this problem right here, the linear velocity of this point P on this body doing rotation with about a fixed axis, the velocity is always tangent to the path. The path of point P is going to be a circular path. So VP is tangent to the path, and its magnitude is determined. How is it related to omega? It equals to omega times r, r being this radius of rotation. And at the same time, P, at point P, we will have two components of linear acceleration. One is tangential acceleration component, which is along the direction of your linear velocity, so it's also tangent to the path. And also another one that is normal acceleration, that is pointing towards the center of rotation. So AT here will equal to alpha r, alpha being the angular acceleration, and then AN component will equal to VP squared over r, which is also omega squared times r. So at this point, if we know that theta equals to 2 pi, we can actually evaluate VP, the linear velocity, equals to omega, which is 0.2 theta squared times r. So theta equals to 2 pi, so 2 pi squared times r is 0.5. So this equals to, if we evaluate it, 3.95 in the unit of meter per second. Per second, not second squared. Okay, so that answers the first part of the problem. But if we want to calculate the tangential acceleration, at this point, we do not know what alpha is. However, we know that angular displacement theta, angular velocity omega, and angular acceleration alpha, they also satisfy the three basic kinematic equations. In other words, omega equals to d theta dt, and then alpha equals to d omega dt, and last one, alpha d theta equals to omega d omega. So in this case, because we do not have any time, we know theta, omega, and alpha. Therefore, out of the three kinematic equations, we pick the last one. So alpha d theta equals to omega d omega. And we can divide both sides by d theta. Therefore, alpha equals to omega times d omega d theta. And that equals to omega times d omega d theta. Omega is a function of theta, so that equals to 0.2 times 2 times theta. At the same time, omega equals to 0.2 theta squared. So multiply all that together. So that equals to 0.2 theta squared multiplied by another 0.4 theta, and that equals to 0.08 theta raised to the third power. Therefore, now we can evaluate alpha. At this point, theta equals to 2 pi. Therefore, this is 0.08 times 2 pi raised to the third power, and that equals to 19.8 in the unit of radian per second squared. That's the unit for angular acceleration. So now we can evaluate AT. AT equals to alpha r, and that equals to 19.8 times 0.5, therefore 9.92. So so that's simply 9.9, and that equals to that has a unit of meter per second squared, and at the same time an equals to omega squared r, which equals to 0.2 times 2 pi squared altogether squared times 0.5, and that equals to 31.2 in the unit of meter per second squared. So now the overall acceleration can be determined by, so the magnitude of the acceleration vector can be determined by at squared plus an square root, and that's evaluated to be 32.7 meter per second squared.